Okay, hello. Hello. I think let's get started. And because I guess probably we're going to be using more time in this week's lecture. Okay, we're going to talking about a new topic called waiting line models. And speaking of the waiting line, I guess everybody in this classroom, including me, have some experience of waiting in a line or waiting in a queue, because that's normal things in daily life. Because if you want to buy a ticket in some other places, you want to go to the ticket hall and wait in a line, and then waiting to be served, and then you buy the ticket, and then you leave. Or you want to buy a coffee, that's normal every morning. You want to buy a coffee, you go to a coffee shop, you wait in a line, and to be served, waiting to be served, and then you have been served, and then you got a coffee, and you leave. Okay, that's normal things every day. So we're going to talk about this very interesting topic. And so the things we're going to talking about is think about if you go into a coffee shop, and have you ever think about why do we have a queue there? So usually we have a queue there. So why do we have a queue? Maybe you are thinking about, oh, we got a lot of people arriving in the coffee shop. That's true, yeah. But why? What is the real reason that we have a queue there? So we're going to talking about that. And if we do have a queue, so how long is the queue on average every day? Sometimes the queue is very long, sometimes it's very short, sometimes no queue. That means zero length. So on average, how long it is? And then, so if you have to wait in a line, waiting a queue, so how long do we need to wait in a queue on average? Because sometimes you go to a coffee shop, you immediately got your coffee. Sometimes you have to wait 10 minutes or 15 minutes later on. So that's basically the things we're going to try to calculate, try to figure out in today's lecture. Okay, let's get started. And I guess maybe this is the first time you see my names in here because I designed these slides, but previously I used Wolfgang's slides. Okay, let's get started. So waiting line models, we're going to spend 2 weeks in here. So most of the theories and formulas and calculation will be discussed in this week with some examples and questions. And in next week, we're going to discuss slightly more advanced topic on waiting line model, and then some more questions, real questions and examples. Okay, 2 weeks on here, and then 2 weeks on inventory models. Okay. So, this is basically the objectives and the topics. So when you try to understand what is waiting line and what is the process, so how many components we can consider, and we try to make this as a scientific problem, not just going there and waiting line. That's quite informal things. And I'm trying to figure out what is the utilization if we consider the whole waiting line system, and what is the arrival rate, what is the service rate, and this is a crucial concept in this problem. Okay, so this is, I think, a very normal picture. It's a very normal scenario of a waiting line. So this is, for example, it's a shop. It's a coffee shop, for example. So you want to buy a coffee. So you go into the coffee shop from here, and you go around. Well, this is not for coffee, maybe something else. So anyway, we think about this is a coffee shop. So you want to go around in here and select the best coffee you want. And then you go here and waiting in the line, or a queue, that's interchangeable. And then you're waiting to be served. And then you're waiting for example, 2 minutes. Then you have been served. You got your coffee, you pay for your coffee, and then you leave. That's very typical things. So in this question, we are basically not considering, for example, you want to spend some time and selecting your coffee, or you want to have a chat with the employees, you want to have a chat with your friends. We are not considering that. We only consider the crucial and basic and fundamental components of a waiting line system. So first, arrival. Because usually we arrive a coffee shop by a random, basically, rate. So if you think about a coffee shop, so you may think about, on average, every hour we could have 20 or 30 or 40 customers, maybe. Because maybe in the peak time we have a 200. But maybe in a quiet time we have 0, maybe. So we can say on average for a coffee shop, maybe we have 20 people per hour as arriving rate. So this is usually the first thing we need to consider. On average, how many people is going to arrive in our coffee shop? And the second one is waiting. So once you go to the shop, maybe you want to spend some time to selecting something, but we don't consider that. So maybe you immediately know what you want. So you go there and then pick the coffee and wait in the line. So waiting in the line takes sometimes, maybe you have to wait for 2 minutes or 3 minutes, or sometimes very quick, sometimes very slow. That depends on how long the queue is. So that's the second crucial component. So how long are you going to wait? So we call this maybe waiting time. So later on, we're going to define this. So maybe the waiting time or just the time we're going to wait to be served. And then you waiting for some time, you could be served. Because the service takes some time. Maybe, an employee prepare a coffee and takes 1 minute or maybe 2 minutes. So you got a coffee. And then service time is the third component. Once you got a coffee, you pay and you leave. So this is very basic things. We only consider 3 things: arrival, waiting, service, and leave. So that's the basic things we consider. So we try to formalize everything as a math model. Consider you are a source. The source could be an entity, could be a customer. So in most of the cases, we consider a source as just a customer. You go into a shop. Usually a shop could have a queue there. So you're going to shop and waiting in a queue. So the customer arriving to a shop and he or she has to wait in a queue. So the customer waits for some time, 5 minutes, for example, and there's a server. Basically, that's the counter. So you want to be served. So you wait in a line for some time, and then you move to the counter. You are served for maybe 2 minutes again, then you leave. So basically, you leaving the whole queuing system. You leaving the coffee shop. That's the basic things we consider in here. And this is the basic model. So later on, we're going to using this graph and maybe more than one time to show the crucial steps, crucial concepts and symbols. Okay, let's take a look on this. Maybe this is a pretty messy and annoying. So this is actually, I think it's a very good graph showing the time relationship between several components. So we're going to looking at this figure and this graph one by one. The first, this direction is time. So think about, so this is a very starting point of maybe 0, starting point of a time, and this is maybe time t, sometime later. So this direction is time. And so at this point, so maybe we got a customer coming in here. So this is a time 0, for example. And so there's a queue and server. We'll consider server as a counter. For example, you want to buy a coffee shop at a counter. So this is just 2 stage. So you go into the coffee shop. So the first stage, or the first state you will be in is the queue. So you go into the coffee shop, and then you stay in this stage. So this is the arriving time. So, and then you have to wait in the queue and wait for some times until you could be served. For example, in here, you could be served. So it takes some time. So we give it a symbol, WN. That's basically the time you're waiting here. So this is a CN, so that's customer number N, the CN customer number N. So, and the counter said, okay, next, that's you. So you go to the next stage, that's you're going to the counter. So then you could be served. So think about in here, that's basically CN minus 1. That's the leaving time of the previous customer. So because if we only have a 1 employee serving there, so the previous customer leaving, and immediately you are the next one. So you go into the server, and you could be served. So the service takes some time, so we call that service time. And when the service is finished, so the departure, so that's customer number N, departs, now leaving, so the coffee shop. Okay, so from here, the customer number N going to the shop and waiting in the queue and wait for some time, and then moving to the next stage, that's the server, and to be served, and then leave. So this is the whole process. So if we consider the whole time, that's the system time. What we call system time, that means including the time you're waiting in a queue and also the time you have been served. So the waiting time and the service time together, that's the system time. Okay, so this is just an illustration of the whole process. So C, that's the customer, and number n plus 1, that's the next customer, next to number n. So the next customer arriving at this time, because it's slightly later on the first customer. So there's basically a time difference in here. So between customer number n and customer number n plus 1. So that's the time difference between the first customer and the second one. So apparently, usually every 5 minutes or 3 minutes, we can expecting a new customer coming in to our shop. So this is what we call inter-arrival time. Sometimes the inter-arrival time could be quite short, 1 minute or maybe several seconds. Or sometimes in a quiet time, maybe every 30 minutes, we got a new customer. So, and after sometimes we got a new customer, and the new customer see n plus 1 going to the shop and waiting here, and wait for some time, and to be served, and serve for some time, and then leave. So this is the path for the second customer. Okay, so in here we have several symbols. We are going to define them later on, but the first thing is we can see there's an inter-arrival time. That's basically the time interval between the customer arriving. So yeah, come on in. So T, that's basically inter-arrival time. And also the waiting time in here. When a customer comes in, so he or she has to wait, and also the service time. So the system time is the waiting time plus the service time. So inter-arrival time is basically correlating to how quickly or how fast a new customer is arriving. Okay, so this is basic things. We're going to define every single symbols, every single concept later on. And when we're talking about a waiting line system, so the first question I want to ask is, why do we have a queue? So the queue's reason is that people arrive because people arrive at a service faster than they can be served. So, for example, every hour we can only serve 10 people, but we got 20 people arriving into our coffee shop. Definitely, we were going to have a queue there. So, what if we only have 1 people arriving every hour, but we can serve 10? So maybe we don't have any queue there. So arriving rate, if that is faster than our service rate, so we definitely have a queue. So later on, you will find out arriving rate and service rate. That's 2 very important concepts. We're going to have to calculate everything based on those 2. And so in this lecture, we don't consider, for example, and the customer gonna not coming into our coffee shop for some time. So we always think about we basically have a lot of customers and coming to our coffee shop. And also we have sufficient, most of the cases we should be having sufficient service capacity to serve all the customer. On the long run, that means on average, we can serve them. But they are not coming in at a constant rate. So that means sometimes we have a quite long queue, sometimes the queue is quite short, so that could be going bigger and smaller, so later on. But we hope to find out statistically on average how the performance is of our service and of the customers waiting. Okay, so this is an interesting figure, but you don't have understands how we're going to calculating this, but we have basically 2 curves. So the black one, that's the departure, and the blue one is arrival. This is to show how a stable queuing system is. So, and this is the time. If at every time point we have some people leaving and some people arriving, and the time difference between them is the queue, the waiting times in here. So apparently we can see sometimes the waiting time is pretty big, but sometimes it's pretty tiny. That means almost no waiting time. So this is a pretty stable queuing system. That means the queue will not be getting longer and longer infinite. So because we have basically a very good service rate, so we can always be serving all the customers on average. So what about this? So apparently this is an unstable queuing system. we obviously have a lot of people coming in here, but we cannot serve them all. So the departure is getting slower and slower, so the queue is getting longer and longer. So in theory, we're going to have an infinite long queue later on. So this is just and this is from the real data of the market, so it can show you how the unstable or stable market queuing system is. Okay, so and when we think about, in this lecture, when we think about a queuing system, and as we talked before, arrival rate and service and waiting line, they are basically three important things. And we only consider those three things. And that's basically relating to the queuing discipline and arrival rate and service rate. So we're going to talk about that later on. Right, queuing discipline, so the order and the waiting customer are served. So in most of the cases, the first in, first served. So that's basically usually the case in normal life. And calling population, the source of customer, we basically think that's infinite. So we don't consider for some times and there's no customer at all and pause for some time and then we have more customer. That's more complicated situations. And arrival rate and service rate, we're assuming arrival rate in most of cases following Poisson distribution or a negative exponential distribution sometimes. So, and what does it mean? We're going to explain later on. And when we're talking about the distributions, how many other possible distributions? So, no, we're going to talk about that later. So there are some notations. So this is all basics of queuing system. The notation is about how we're going to define a queuing system. Usually we have a lot of letters in here. The first three letters are most important, A, B, and S. The first one is arrival distribution and departure distribution and number of services. So the number of services, you can consider that as how many employees waiting there in the counter can serve us for a coffee. So maybe 1 or 2 or 3. And in this lecture, we only consider 1. And the next lecture, next week, so we consider for multiple servers. So most of the cases, we consider arriving and service. So arriving, distribution, and departure and distribution. That's following exponential distribution. And in this lecture, we consider just single server, only one employee there serving us. And we have infinite customer arriving in here. So, when we're talking about exponential distribution, so that means we can also assuming some other distributions. And this is Erlang distribution or some others. But most of the cases, we assuming exponential distribution. We also call that Markoving. So this is Markov. So that's the reason we have an M here. So if we have an M here for the arrival distribution and departure distribution, so we can define MM1. So that means Markoving distribution for arrival, Markoving distribution for departure, and one service. So that's when we say MM1, that means this type of queuing system. And in next week, so we're going to talking about MMC. C means so how many customers. So usually C could be 2 or 3 or 5. That's later on talk. Okay, so that's how we're gonna define our queuing system. So, and once again, I want to do some summarize of the assumptions of the basic single server models, infinite calling population, so always have some customer arriving in, first come, first service, and Poisson arriving, so sometimes that equals to exponential and also exponential service time. Okay, so let's get started to define something, because previously that's all basic things. The first, arrival rate. So when we speaking of the rate, that basically means how fast it is. So arrival rate, the basic definition is how many numbers of customers arrival in our shop for certain time period. So usually we could define this as C/H, that's customer per hour. For example, we can have 10 customers arriving every week, every hour on average. So that doesn't mean every hour we must have 10 customers. But sometimes 10, sometimes maybe 60, sometimes 0. But on average, we can have 10. Okay, if we know the arriving rate or arrival rate, so can we know arrival rate is how many customers per hour? Can we know how, yeah, please?
What's poison arrival rate?
Poison arrival rate? That's basically a distribution. So usually we assuming arrival distribution follows exponential distribution. And exponential distribution is the Poisson is a special case of exponential distribution. Okay, and so as a general definition, we can say so arrival distribution and departure distribution, they all following exponential distribution. And another name for exponential distribution is Markovian. So that's the reason we have an M in here. So MM1. Okay, so. Okay, so when we know how many numbers of customers arriving and per hour, so we can basically calculate or find out so how many hours we can expect one customer. So that's basically equals to 1 divided lambda. So lambda is the arrival rate. So that definition of this is the average time of arrival per person. So usually that's H/C, that's hour per customer. So how many hours we can expect one customer arriving. So, and that's also equals to the inter-arrival time. So think about that. So how many, for example, if 30 minutes we can expect one customer, that basically means on average, so the time interval between the customers are 30 minutes. So every 30 minutes, we have one more customers arriving. So arriving rate, lambda, that's the most important things. That tell us how fast we can expect the customers arriving. And the next one is the service rate. So we also define service rate the same, customer per hour. That means how many customers we can serve per hour. So if we can define that, for example, if we can serve 12 customers per hour, can we find out, so on average, the service time for each single customer. So that's basically the service time and average time for serving per customer. So that equals to the inter-arrival time. So hour per customer. So for example, for every customer, maybe we have to serve 30 minutes. So that's our service time. So when we have a service rate, so that's defined as mu. That's a Greek letter. So we're using 1 divided by mu. That's our service time. So those four concepts are basically the most important things. And also, the customer must serve faster than they arrive. So that means that our service rate should be higher than our arrival rate. So I think that's pretty easy to understand. If we have 10 people arriving every hour, we can only serve 5. That means we are going to have a queue there and longer, getting longer and longer and longer. So we have to make sure if we maintaining a coffee shop, we have to make sure if on average every hour we have a 10 customer arriving, we have to serve more than that. So to maintain a stable queuing system. Okay, so this is the first things we have to understand. So let's do some warming up exercise. So what if we have expected inter-arrival time 10 minutes? So that means on average, every 10 minutes, we expect one new customer. So what is the arrival rate? That's basically 1 divided 10, because this is the inter-arrival time. So that means every 10 minutes, we're going to have one customer. So how many customers we're going to have in 1 minute or 1 hour? So we're using 1 divided by 10, because at 10 minutes, so that equals to 1/6 hours. And so basically we got 6 customers per hour. So just 1 divided by this. Okay, the next one. So if the expected service time for every single customer is 2 minutes, what is the service rate? So how many customers we can serve? In 1 minute or in 1 hour? So it's pretty simple. So we could using 1 divided by 2 minutes. So 2 minutes equals to 2 divided by 60 hours. That's basically 30 customers per hour. So So if you think about this, if every single customer need 2 minutes, so in 1 hour we got 60 minutes, how many customers we can serve? That's quite simple, just 30. Because if we times 2 and 30, that's 60 minutes. 60 minutes is just 1 hour. Okay, so now if we know the arrival rate, for example, 3 customers per hour, on the service rate, for example, we can serve 4 customers per hour. So we can define a new thing called utilization. We're using U or rho here. That equals to lambda divided by mu. So arrival rate divided by the service rate. So on this case is 3 divided by 4, 75%. So what does it mean? So that means every hour we have 3 customers arriving, but we can serve 4. So that means we can serve more than the arrived customer. So that means on 75 of the time we are working to serve the customers. But because we can serve 4, so that means we got 25% of the time idle there, because we only got 3 customers arriving. So that's basically the means. Utilization of our serving system is 75%. So because on average, 70% of the time we are working, and the other 1/4 we just idle because then nobody coming in here. Okay, if we know this, we're gonna doing something slightly not very easy to understand, maybe. Okay, so this is, don't panic, it's not a snake. It's something we call a Markov chain. So what does it mean? So we have 0, 1, 2, and 3, 4, 5, and k minus 1, and k, and so on and so forth. We can have a quite big numbers in here. 0 means we have 0 customer in the whole system. So when we say a system, you can understand a system as, for example, a coffee shop. So 0 means the state of the coffee shop is 0 customer. So we don't have any customer in a coffee shop. And so we have arriving rate, lambda. For example, lambda could be 3 or 3 customer per hour. We can have some customer arriving here. So, and then later on we have 1 customer because people arriving. So 1 in here, that means we have 1 customer in our system. 2 means 2 customers in our system, and so on and so forth. The k means k customers in our system. Okay, but we don't know. So maybe for some times, and a lot of customers arriving at the same time. For example, a football match is just finished that people want to have a coffee. Usually they don't want a coffee, they want a beer. But maybe sometimes they become very rational. They want a coffee, so they come into the coffee shop after the football match. Immediately we got 1,000 people arriving here. So that means immediately so the state of the system jumping from 0 to some other state. Okay, so this is showing how the state of our system, that's basically of our coffee shop, is changing. Okay, because we always having an arriving rate. This is average arriving rate. Okay, now and think about the probability of the whole system staying at 0, state 0. So that means what is the probability of our coffee shop have no customers? So if we hope to find that, how to do that? So if we hope to find out the probability of having no customers there, so that's basically we only consider this, just 2 states. Because I think about, if we hope to find out the probability of have no customer there, 0 customer there, so we have to think about how we're going to maintain that. So how to maintain that? If we always want to maintain no customer in our coffee shop, that means we have to serve the customers very, very quickly. So once we got a 1 new customer, so we serve them immediately, so the customer finished and leave. So and another one coming in here, so we serve very quickly and they leave. So that means if for some reason we have a fixed lambda arriving rate, so all we can do is we're going to have to increase our mu, that's the service rate. We're going to increase our service rate, so we're going to serve very quickly, so because we could do every work very quickly, so that means we can always finish our job in a very short time, so we can make the customer leaving. So that's the only thing we can do to maintaining our coffee shop have 0 customer. So if we hope to do that, we have to maintain a relationship. relationship is the probability of having no customer times the arriving rate. That should be equals to the service rate, mu, times the probability of having one customer. Because the higher the service rate is, the lower the probability of one customer is. Because you're serving the customer very, very quickly, so that means that's very tiny probability our system only have one customer. Because once we got one customer, and immediately he leaves. So the probability of P1 that could be quite tiny is in here. But if we hope to maintaining the system of this, so we have to maintaining this relationship because we always have customer coming in here by a lambda rate. And then, so we're going to make him or her leave immediately by increasing our mu. So that means we're going to decreasing P1 and to a very tiny, tiny probability number. But P0, for some reason, that might be not controllable by us. Because we don't know because how the people are arriving from the markets. So we cannot control this. But we hope to maintain this. And the only thing we can do is increase the mu to a very high number. And at the same time, the P1 is decreased a lot. So we're going to maintain this relationship, trying to maintain the whole coffee shop having basically 0 customers. But one thing is, so that doesn't mean P0 and P1, so the probability of a 0 customer and probability of a 1 customer, we plus them, that equals to 1. No, it doesn't mean that. Because we always have maybe tiny probabilities to have more customers. For example, if we have 500 people arriving at the same time, so that means so we're going to jump into some more states immediately. But the probability might not be very high, but so that still there, we got some probability of having more and more customers. We don't know how much it is, but there's definitely some probability. So this is not 1, but this is the relationship we have to maintain to make sure we only have 0 customers there. If we have this relationship, for example, so that's very easy. We can calculate this, P1. So the probability of a 1 customer, that equals to lambda divided by mu, so the arriving rate divided by our service rate times the probability of 0 there. So let's think about example. If we basically have, on average, 10 customers arriving, and we're working very hard, so we can serve 60 customers per hour. So if probability of 0, and that's probability of no customer is 80%, so basically we can calculate the P1 as a pretty tiny percent, around 13%. So basically that's coming from this relationship and how we hope to maintain 0 customer in our coffee shop. Okay, if we have this relationship and think about what if we want to maintain only 1 customer in our system as a stable system. So 1 customer is in here. So 1 means we only have 1 customer. So this is a special case, special state for the whole system. If we hope to maintain only 1 customer stable there in our system, so we have to consider this because we have 0, this is 1 state. We can jump into state 1 from 0. We can also jump into state 1 from state 2 because we finish serving 1 customer from 2. So that means our system will have 1 customer leaving, and then our system have 1 customer and still remaining in our system. So by mu, the service rate in here. We can jump into 1 from 2. We can also jump into 1 from 0. So if we hope to maintaining this, so basically we have to maintaining this relationship. So how do we understand this? So this is basically means the jumping into, so the rate jumping into state 1 should be equals to the rate jumping out of state 1. So think about, so P0, if we stay in here as state 0, no customer, so basically if we no customer is in here, so the customer arriving by lambda, it's arriving rate. So we times that. So that's the one way jumping into state 1. There's another way. So what if sometimes we stay in state 2, and we could also jump into state 1 if we finish serving 1 customer by mu, that's our service rate. So mu times P2, so probability of staying in 2 times our service rate. So this is a two-way we're going to jump into state number 1. So that should be equals to, because the flow in should be equals to flow out, that should be equals to how we're going to jump in out of state 1. So apparently, if we stay in state 1, we can jump into state 2 if we have a new customer arriving by lambda. So P1, that's the probability we stay in state 1. But what if we got one more customer, a new one? So by lambda, that's always be the rate of arriving. So we times that. That's one way we're going to leave in state 1. And then there's another one is what if we stay in state 1 and we finish serving the current customer? So the customer leave, so this the service rate is mu. So P1, that's probability of staying 1 and leaving. So we're gonna go into there. This is another way going out of from state 1. So the probability of going to state 1 should be equals to the probability of going out of state 1. So if we have this relationship, we can maintaining only one customer in our system. Okay, so if we have this relationship, so apparently we can try to do some calculation because we try to move, because we know P1 is equals to lambda divided by mu times P0. So we can just substituting P1 to here and reorganizing P2s together and to find out the relation between P2 and P0, and we find out that is the relationship. So between P2 and P0. Okay, and so if we keep doing this for more and more, finally, and we can find out pk should be equals to this. So we can basically replicate the relationship from 2 to k, because that equals to lambda divided by mu with the power of k times p0. So that's a very interesting relationship. So what is pk? That's basically the probability of k customers in the whole system or in our coffee shop. So that's determined by, basically that's determined by our arriving rate. So it's not controllable, but we can control our mu, the service rate, and also P0. So that's basically 0, no customers in our whole system. So that's more or less determined by the whole market. Okay, so, and this is how we're going to find out the relationship of the probability of certain customers in our whole system. And if we have this relationship, so think about, because we define lambda divided by mu before, that's basically the utilization of the whole system. So we can write rho. Rho is the utilization with the power of k times P0. That's equals to probability of k customers. If we have this, think about what if we hope to find out the probability of all customers. So how many customers we possibly have in our system? We don't know. Maybe 1, or maybe 2, or maybe 3, or maybe 100, or maybe 1,000. That's possibly. So the probability of that is very low, but it's still possible. Sometimes we can have 1,000 customers. So we don't know what is probability for all customers. But when we say all, in theory, that means from 0 to 1, 2, 3, 4, 5, and to infinite. Because we don't know. Because mathematically, we should be able to have infinite customers. So if we hope to find out the probability of all customers, so because for every single one, that equals to rho with the power of k times p0, that's pk. K should be from 0 to infinite. So if we add them all together, so that should be equals to 1. So that's the total probability theory. So because we don't know, so probably we have, most of the cases, 2 or 3 customers in our system. That's higher probabilities. But for our system have, for example, 5,000 people, that's tiny, tiny, tiny probability, maybe 0.000001, but still there. So in theory, if we add all possibilities there, that should be equals to 1. So that's an interesting relationship. So if we have this, relationships in here, so probably we can try to find out what is P0. So because we hope to add from k from 0 to infinite. Because we know p0, that's basically a constant. So, and we can just take p0 out of the sum. So p0 in here, and so we have to calculate the sum of this. Rho with the power of k from 0 to infinite. So how to do this? So apparently, we can make p0 equals to 1 divided by, and this. This is a sum of a certain series. Finally, we got this. But how to do this? So apparently, we should try to calculate the sum of this. So I guess you should be able to do this because this is a geometric series. So try to find out the sum of a geometric series. So, and just try to refresh your memory. So we can make the sum of this as S. So what is S? S is basically rho with the power of 0, that's 1, plus rho squared plus rho with the power of 3, and so on and so forth. So an easy way to calculate that is we times minus rho on both sides, on here, and also in here, and times minus rho. So left-hand side, if you times minus rho, that's minus S rho. And by right-hand side, if you times minus rho, the first one becomes minus rho. The second one becomes minus rho squared. And the third one is minus rho with the power of 3, and so on and so forth. We have negative symbols in here. So if we add the two equations together, we can see right-hand side, we can cancel them all. So basically, all canceled. So we only have a 1 in here on the right-hand side, but left-hand side, we have S minus S rho equals to 1. And finally, we got S equals to 1 divided by 1 minus rho. So this is a quite basic mathematical and deviation. So if we have an S in here, so P0 equals to 1 divided S. So that basically equals to 1 minus rho. So is it interesting? Because the probability that we don't have any customer equals to 1 minus rho. So what is rho? Rho is basically defined by lambda divided by mu. So that means the probability of having no customers is basically determined by arriving rate and service rate. So lambda and mu. Okay, does it make sense? So let's take a look. If lambda is a 3, that means what? We can serve, we have 3 customers arriving in 1 hour. So if mu equals to 4, that means what? We can serve 4 customers in 1 hour. So apparently rho equals to 75%. So we've done this before. So according to this equation, so P0 should be 0.25, just 1/4, 25%. So 25% that we have no customer in our system. Does it make sense? So if you think about, on average, we can serve 4 customers in an hour. So the simple way is, so this is a 1 hour, 60 minutes. We divide it by 4, but this is not correct, but just show some illustrations. So we can serve 4 customers. So basically, we can serve 1, 2, 3, and 4. But we only have 3 customers arriving in an hour. So then that means maybe we have 1 customer, another customer, another customer. Only 3 in 1 hour. Okay, that means, so 3 over 4, 3/4 of 1 hour, we have to work to serve our customer. But we only got 1/4 of time free. That is here. So that means the why we are free, because we don't have any customer arriving in. So that's P0. So probability of having no customers is 25%, which is 1/4. So that's the basic illustrations of why we have P0 equals to 1 minus rho in here. So that's an interesting relationship. Okay, so, and this is the probability. Usually there's one crucial thing, because in here we have some descriptions on how many customers we can serve, so how many customers arriving. So one more thing is we have to have this on average. So, because this is not a must number, so we couldn't guarantee 4 customers in 1 hour. We can serve that. We couldn't guarantee 3 customers. We have to say everything on average. We can serve 4 customers in an hour on average. we have 3 customers arriving on average in 1 hour. So don't forget on average. This is crucial, especially in your final exam. You have to write down on average. So, because we just calculated the probability. So in statistics, after we calculate the probability, the next topic is always be expected value. Because we try to review the expectations in last lecture. So what is expectation? Because we got some values, we got some probabilities, and then we can try to find out the expected value of the whole, random variables or random systems. Okay, and we just calculate the probability of every single customers for 0. There's an error popping in here. Okay, never mind. Okay, so we just calculate the probability of 0 customers, 1 customers, and k customers. That's the probability. And also we know the numbers of customers, 0, 1, 2, 3, 4, 5, and 2k. So how to calculate the expected total number of customers in the whole system? When we see the system, that also means the whole coffee shop, including the people in the queue and including the people being service. Okay, so that's the basic formula. So why we have this? Because k, that's the number of customers in the system. We could have k equals to 0, 1, 2, 3, 4, 5, and 2k. So and to maybe large number to n. And if we have 0 customer, we have p0. That's the probability we have 0 customer. If k equals to 1, p1, that's the probability we have for 1 customer. So we have to times the value, so that is k, that's the number of customers in our system, with the probability of that number of customers in the system together and add them all. That's basically the expected total number of customers in our system. But the problem is how to do this. So we got some formulas before. Think about k is still k here, but pk, what is pk? Pk could equals to 1 minus rho, that is p0, times rho with the power of k, and rho is lambda divided by mu. So this is the formulas we've done before, so we can substituting everything into here. So now we need to calculate for k from 0 to n. So basically 1 minus rho, that's a constant. We can try to take rho out of the sum, and like this. So apparently we can take 1 minus rho out of the sum, but we can take 1 more. So rho with a rho in here, so that means k rho have a power of k minus 1. So, and also we got k's in here. So if you're looking at this, is it something you've seen that before? So that's basically, so if I jumping from this step to the next one, I don't know if you could understand this. Because if you're trying to think about, if you hope to calculate some first degree derivative of rho with the power of k, that basically having the result of this format. So that's basically how we're gonna derive the 2 steps. So if we have this, if we're trying to find out basically the first degree derivative of rho with the power of k, so that equals to k with a rho times rho with the power of k minus 1. So this is pretty simple. If we add the sum symbol to both sides, so we can have this. So if you're looking at the left-hand side, so that is here. If you're looking at the right-hand side, that's basically this part. So that's equal, so we can substituting this to here. So why we want to do this? So because also, if you learned the calculus before, so you know the sum and the first degree and derivative, that could be interchangeable. So we can change them, change the direction. So we can try to do the sum before the first derivative. Okay, so the reason we hope to do this is actually we have done the sum before in the last slides. So, and that's basically, we jump into the final result. So how to do this? That's basically from here. So if we hope to calculate this, if we hope to calculate the first degree derivative, so we're going to have to calculate this. So this is sum, because we've done this in the last slides. So that's equals to 1 divided by 1 minus rho. So then we need to do the first degree derivative of this 2 rho. And that is the result. I guess you should know how to do this. No, you don't know. Okay, fine.
I believe a large number of people have never studied derivatives before.
I guess, but I try to write something down in here. So this is basically based on a change U, because we hope to do, let's think about, okay, this is something we hope to do. We hope to do D rho, and with basically we call them G. Okay, so but G, what is G? G here is 1 minus rho. So that's basically a very typical formula of 1 minus y. So, because in y, that's equals to 1 minus rho in here. Okay, so we have to do step by step. So we have to do, if we want to do dg d rho, that should be dg to dy and dy to d rho. So this is called change U. So if you want to do this as a first step, so this is the basic step, basic format of G. So we got y, so dg to dy, that's basically, because that equals to y with the power of minus 1. So if you want to do this, so dg to dy, that's basically equals to, you're going to have to move this out of to here. So that's basically minus 1, yeah, minus 2. Okay. But what is y? Y is actually this. So later on we're going to do this. So what is dy to d rho? So dy to d rho, that's pretty simple because this is a constant and this is just rho, but we got a negative things. So that's basically equals to this. That's pretty simple. So okay, so if we're substituting everything to here, so you have d and g, that's d rho, that's equals to basically 1 and minus times minus 1. So that's the reason you should have, sorry. Yeah, that's basically how we're going to do this. Is that slightly more clear? I don't know. Okay, so that's basically a change U here, because you got G, that's this. And we're trying to do this, and first derivative of G to Y, and Y is 1 minus rho. That's 1 is constant, so we don't have this. And it's 1 minus rho, because we have a negative 1 here. So we got negative, negative, so we have Y with the power of minus 2. Okay, so that's why we have this result seen here. And we can substituting this result back to here, and then we got the final result because this is 1 minus rho and then 1 minus rho square. We can cancel this. So we can rho divided by 1 minus rho. And this is how we're going to calculating the total expected total number of customers in our system. Okay, question, please.
So could you just show the steps to prove the formula?
Yes.
So we don't have to do it in the exam, we're just doing the formula.
I say you should do. No, just joking. You don't have to do. You don't have to do all the calculations, and you don't have to prove the formulas in here. And I guess maybe the next question is, shall we remember all the formulas in here? I guess that's probably the question. So I'm going to show you later on. I'm not answering this question now. So, and this is basically how we're going to find out the relationship. So L, that's the average number of customer in our whole system. So when we say system, that including queue and service, 2 parts. So And because row, so we know what is definition for row before, so this is row. If it's substituting rows in here, so we can basically having thus. So L is also equals to lambda divided by mu minus lambda. So and mu lambda, so that's two basic things and two most important things. That basically means how many customers going to be in our system on average, only determined by rate and service rate. Two things. Okay, so don't hate me. And this guy did all of those. So that is that he's a mathematician called Erlang or whatever. So he developed everything for the MM1. So before he find out, okay, so this is how we're gonna find out on average how many customer in total in our whole system. Okay, so I guess maybe we should have a rest for 5 minutes, and then we're gonna coming back for even more complicated things. Okay. So 5 minutes, try to be back at maybe 10 or 5 past 10, okay? Okay, so let's get started again. So hopefully those things is not too much horrible to you guys, but you don't actually need to remember every single step of this, how L is derived into the last one. But you should know what is mu defining here, what is L, what is lambda, what is mu, because anyway in a final exam paper, it's not possible to write down very clearly on the paper, say L is the expected total number of customer and lambda is the arriving rate, and now the lambda is 5, mu is 6. What is L? That's too simple. That's elementary school. So usually in the exam, you'll be given a story. For example, a coffee shop. So I give you a story. So on average, every morning we have blah, blah, blah people arriving, and we have several employees there and serving and on whatever rates. And then you should calculate. And maybe I'll give you some challenges. For example, we only have 2 employees there. Shall we hire more employees to make sure we can satisfy the customers and requirements? So try to maintain a queue as shorter as possible. So this is something like, but this is, we're going to talking about that later on in this lecture. So let's try to moving on to the next topic. Now we calculate what is L. L is the expected total number of customers in the whole system. And this is from one mathematician called Erlang. So, and the bad news is we got another mathematician. So, and the surname is Little. So we call that Little's law. That doesn't mean and he's little. His name is John. He's a very, very famous mathematician in operational research area. So, and he figured out L. On average, the total numbers of customers in our system, that should be equals to the arriving rate times the mean system time. When we say system time, is the time this customer stay in our coffee shop in total, including waiting in the queue and including the service time. So in total time, the customer staying in the whole system times arriving rate, that should be equals to L, the average number of customers in our system. So why we have this? So basically the proving process is more complicated. So we won't do that. So, but intuitively, so this is the reason, because we don't create any customers inside our system, or we don't lose any customer inside our system. We only have one entrance there and one exit. So basically the customer coming to our system with serving and then leave. So we don't create any more. So basically that means, so the time, for example, you can think about if every customer is going to stay in our system for 15 minutes, that's 1/4 of hour. And every hour we have 4 customers. And so basically 4 customers per hour, and every customer, so 1/4 hours. So in average, so we are going to have just 1 customer in our whole system. That basically makes sense. So we can try to think about this using the following examples. So what if we have lambda equals to 3 customers per hour? We have a 3 customer arriving in an hour on average. So, and the customers stay in the system, and both queue and service is basically 15 minutes in average. So, and 15 minutes, so that's basically not very long. So we have 3 customers per hour times 15 minutes and divided by 60. That's basically how many hours? So, and then we times them together. That's basically 0.75 customers. It's not less than 1 customer on average in our whole system. Why we have this? Because think about this. So the whole system time, and so it's 15 minutes divided by 60 is 1/4 hour per customer. So basically the customer stayed 15 minutes and a quarter of hour. And smaller than inter-arrival times, because every hour we only have 3 customer, but 1 hour we can serve 4 customer. So that means, so basically we can serve more than the arrived customer. So that means in our whole system, we shouldn't have 1 customer, more than 1 customer waiting there in our system. So 0.75 customers on average. So that means, okay, we're having pretty good system. So, and that's the intuitive proof of this relationship. So now we have one more, and basically one more symbol. We got L, and we got lambda, because the lambda is the first symbol we introduced in this lecture. That's the arriving rate. L is the, on average, that's expected total number of customer. And W is the expected time of the customer we staying in the whole system. Okay, if we have this, so L equals to lambda times W, W is the time, and also we have this, L equals to this. This is from another mathematician. So that basically means, and we could have, this is one relationship, and this is another relationship. They are both equals to L, so we can make them equal. So we can cancel the lambdas from here, and we can find out. And W, that's basically the average time of customers stay in the whole system is only determined by mu and lambda. That means, so how much time you want to stay in the whole system? That's only determined by the service rate and the arriving rate. That also makes sense, because if we're serving the customer very, very quickly, so apparently the customer will stay in our system very short time. But if our service is very, very slow, apparently so the customer is going to stay in here for a very long time. Okay, let's take a, so let's think about this. This is basically an example. So what if we can have 24 customers arriving per hour on average? We could serve 30 customers per hour on average. So how many hours is the customer going to stay? So that's basically from this formula, mu minus and lambda, that's basically 1/6 hours. So that's basically a quite short time, so the customer will stay in our system. Okay, so this is an L equals to lambda times W. But so far, we're talking about the whole system. So the lambda is arriving rate, and L, that's basically is the total number of customers in the whole system. W is the customer average time customer stay in the whole system. But the problem is that, and this equation is also holds for either queue and server. So, because we only consider waiting and service, 2 things in our queuing system. So if we consider the whole system, we have L equals to lambda times W. So W is the whole system time, and L is the whole system, and number of customers in the whole system. And so what if we consider queue and service respectively, 1 by 1? So we also have this formula seen here. So that means average customer in the queue, LQ, equals to the arriving rate. We only have 1 arriving rate, that always be the constant, and times the waiting time in the queue. So average waiting time. So that's WQ. We have queues in here. That's for the queue. And the server. So the average number of customers in the service are being served. So LS, S represents the service, equals to the arriving rate, lambda. Lambda is the same. And times the WS, so the waiting time in the service. So the time in the service is not waiting time in the service. So basically, that's the time in the service and times lambda equals to the average customer in the service, and time of waiting the queue times lambda equals to the average number of customers in the queue. But the problem is that how to find out LQ and LS? So we're going to try to calculate. So before we try to calculate, so let's revisit this figure again. So we saw this graph before. So this is the system we are considering. So we have one customer coming to the coffee shop and waiting in the queue. So we're using LQ represents the customer in the queue. And the WQ represents the time in the queue. And LS, that's the customer in the service. And WS, that's the time in the service. So WQ plus WS, that equals to W. W is the total time in the whole system. That only contains WQ and S. And so L is the total customer in the whole system. That only contains two components, LS and LQ. So LS is the customer in the service, Q is the customer in the queue. So that's the basic relationship. So we only consider two things, waiting and service. Okay, let's think about service and queue one by one. So what about the service? We know the service rate. Usually, we know what is mu. So how many customers we can serve for 1 hour? So if we know the service rate, can we calculate how many hours we can a customer need for the service? That's basically the average service time for one customer. If we know how many customers we can serve in 1 hour, we can calculate how many hours we can serve one customer. That's basically equals to 1 divided by mu, that's WS. So very quickly, we get one thing. So this is the average service time for one customer. That just simply equals to 1 divided by mu. And we also know LS equals to lambda times WS, because we got WS in here. So lambda times WS, that equals to lambda divided by mu. Interesting. Did you see this before? Yes, we did. So this is actually the utilization. So that basically means the average number of customer in service. That's equals to the value of the utilization, because we have the same equations in here. So all from lambda divided by mu. So that's also determined only by the service rate and arriving rate. Okay, so that's for the server. And so ARS equals to mu. That's for the server. So what about the queue? Because we know WQ, that should be equals to W minus WS. So because we know W and WS, if we know them. So we can basically calculate WQ equals to W minus WS. And what is WS? So WS is the average service time. It's in here, so we got this. And W is because we got this formula before in the previous slides. So we can basically calculating and by using these formulas. And at the same time, we know LQ equals to lambda times WQ. WQ is the time, and this is the average customer in our queue. So basically, we can try to using this or this to calculate. So WQ, if we have the W and in here and that minus WS, WS is the mu minus 1, so we can have this result. If we have the WQ thing here, so LQ equals to WQ times lambda again, because from this equation, so we can finally have the average number of customer in our queue equals to this. And also, you can calculate the average number of customer in queue by another way. What if you know L and LS? Because we know this is the relationship. So what is LS? Because we know LS is row. It's just a utilization. So L minus row. So what is L? Because we calculated L before by previous slides. So if you're using this, we can get this equation. They both the equation for LQ, so average number of the customer in the queue. So later on, you can try to prove, is it the same? Actually, they are the same. So if you're substituting what is mu, mu is lambda divided by mu. What is rho? Rho is lambda divided by mu. If you're substituting this into this formula, you will definitely get this one. So this is the equations for and the expected number of customer in service and queue. So we got a lot of formulas in here. So let's try to do some summarize. So at the very beginning, so we know, what if we know the arriving rate, lambda, and also the mu's in here, that's the service rate. So if we know everything, so we can, we can define the rho, that's a utilization. And also we can try to calculate what is probability of having no customer in our system. That basically equals to 1 minus the utilization. That's at the very beginning, we try to prove this. And we got this. And then we're trying to find out the average number of customers in the whole system. And we got two mathematicians. So the first one, and he believes L could be calculated using this, because we tried to derive this, because he tried to derive the average number of customers from the probability. So we can calculate a probability and times the number of customers, and we sum from 0 to infinite, and we finally got this number. And we have another mathematician. He believes the average number of customers in the whole system equals to the arriving rate times the time the customer stay in the whole system. So apparently they are both correct. So if we relate them together, we can have the W equals to mu 1 divided by mu minus lambda. That's basically determined only by arriving rate and service rate. So, and now for little, so law, we have L equals to lambda times W. That's for the whole system. And so if we're using this formula for the queue and the server respectively, we can have two additional equations in here. So for queue and server. So let's start it with server. Why we started with server? Because we know the service rate for most of the cases. It's slightly easier to get the service rate, because the service rate is mu. We know how many customers we can serve per hour. So we can basically calculate how many hours we can serve one customer. So that's basically WS. So how many hours we can serve one customer, that equals to how long this customer will be stay in the service. So that's the service time. So service is 1 divided by mu. And then if we know this, we can basically calculating times lambda times 1 divided by mu, we got this. So we find out the average number of customers in the service that equals to the utilization. And later on, if we know everything for service, so we can try to calculate everything for the queue. Because if we know WS, so we can calculate the WQ, so that's basically from the total and time minus the time in the service. So we can have this. And then we can try to substituting this into the LQ. So where it is, so this is basically the W. W is from here. So we calculated W before, and we know W, that's the total time. And also we know 1 minus mu, that's basically the service time. We can get the queue time. So the time the customer stay in the queue. And we know the customer stay in the queue, so times lambda, we can get, this is the average number of customer in the queue. So, and at the same time, we can try to calculate the customer in the queue by using the total customer number in the whole system minus the customer in the service. So because customer in the service equals to the row, so we can using row divided by 1 minus row. And where this is from, and this is actually from above, so this is this, so bad. Sorry for this, I'm gonna erase. Okay, so this is actually from here. Okay, so we got what is L, and then we could basically substituting the L's in here minus row. Row is LS. That's the number in service, and we got the number in queue. So, and to do this, the assumption is that so the total time equals to the queue time and the service time. The total number of customer equals to the customer in the queue and customer in the service. So this is the assumption. We only consider 2 components in here. Okay. Shall we remember all the equations? So too many things. So we're going to show you later on. But before we show that, so we're going to try to do some more exercise. Think about this. Okay, what if we know lambda and mu? So 24 customers per hour arrival and 30 customers per hour can be checked out. So that means we can serve 30 customers. So the first thing we can calculate is the utilization. That's pretty simple. 24 divided by 30, that's 80%. So 80% of the time, the people are quite busy because we got customer arriving in, and the other 20% of the time, the whole system are idle because there are no customers. Okay, is the system stable? It is stable because it's smaller than 100%. If we calculate utilization is higher than 100%, that means we are going to have a queue getting longer and longer because this is not stable because our arriving rate is higher than our service rate. But for this case, it's quite stable. Okay, and what is the probability that the system is idle? 20%. So we have 80% of utilization. That means another 20% of the time we have 0 customers. Okay, so and what is the probability that no customer in the system? That's same as the previous one, 20%. Okay, so that's pretty simple, isn't it? How many customers in the shop? So it's quite easily using this equation because we only determined by the arriving rate and the service rate. 4 customers on average, and we can using this again. This is 80% divided by 20%, so this is 4. How much time they spent there? So this is the total time the customer spent in the system. That's basically L divided by the lambda. L is 4 customer, divided by the lambda. Lambda is 24 and per hour, so it's 1/6 of an hour. That's basically 10 minutes on average. How fast is the service? So that means, so what is the service time? So that's another way to asking what is the service time. So service time is 1 divided by mu, because this is the service rate. We can serve 30 customer an hour, so we can basically use 2 minutes for 1 customer. Okay, so how many customers in the service? So that's basically LS, and that's basically equals to the utilization, because we've done this before. How long they have to wait? So that usually means the time spent in the queue. So that's equals to the total time minus the service time. 10 minus 2 is 8 minutes in the queue. How many people are waiting? So how many people? So that's basically waiting. That means in a queue. So we got LQ equals to lambda times WQ. This is the arriving rate. We got the time. So that's basically 3.2 customers on average. So this is pretty simple calculations. If you know the equations, you could very easily to calculate that. And then we're gonna move into the next one. So this is actually a real final exam question in last year. So, okay. I guess you may take 1 minute, maybe. Try to read through all the topics, but we are not covering 100% covering all the knowledge. Just and in this question, we still need you still need some more knowledge in next week's lecture. So, but if you're looking at here, so this is the formula. This is also part of the final exam papers. So you will see you will get some equations, not all, but those equations are for MMC. MMC, that means we have more than one counter, more than one service. So we're going to cover MMC in next week. But for this week, this is just MM1. This is a special case of MMC. So basically, you have those equations, and you have how to calculate the average number LQ in the queue. So this is more complicated than today because we're going to have to consider more than one and service. So that's the equation we're going to discuss later on in the next week. But those are basically the equations that will be given in a final exam paper. So you will have some reference on those equations, but you have to understand what is L, what is lambda, what is LQ, and what is U, what is LQ, and what is P0. If you don't know that, that's going to be a problem. Okay, and for now, let's take a look on the question. So customer arrive at whatever sea cargo, and they take a number and wait, so that's basically queue, to be called to pick up their goods from employees. So that's basically a logistic system. And from the experience over the past years, the store's manager knows the customer arrives at a rate of 40 per hour on typical average day between this time. So that means what? So that's basically giving us information of arriving rate, because it is quite clear the customer arrived at a rate of 40 per hour. So, and between a certain working time. And a single employee can serve 15 customers per hour on average. What is this? So 15 customers, this is basically service rate. So we know arriving rate, we know service rate, and then we keep rating. So this shop wants to make sure customer wait no longer than 10 minutes for service. That basically means they hope the time the customer waiting in the queue should be no longer than 10 minutes. Okay, hence the shop is contemplating to employ 3 people. So today we're not considering 3 people. That's basically multi-service problem. So, and for today, we only think about the first question, and because we don't cover the second and third one. And 3 people, later on, we're going to consider this. So I want to show you, so for this question, we have 25% of the mark for the whole final exam paper. So the first question is 9, second is 8, and the last one is 8. So you can see, so the first question is very simple, but it contributes 9. So take a look. What is the first question? State arrival rate. I think you could very easily do this. What is arrival rate? So we told you 40 customers per hour. Arrival rate, lambda equals to 40 customer per hour. Attention. So in the exam, you have to write C/hour or customer per hour. You cannot just say, okay, arrival rate 40. You won't get the mark. 40 what? 40 customer per minute or 40 hour customer per day? So you have to write down the unit, 40 customer per hour, because this is showing in here. Sometimes the question will show maybe 5 customer per minute, something like that. If you only write down 5, what does it mean? So you have to write down very clearly what is the unit. Okay, so this is for the first and tiny question. Second one, service rate. Service rate, 15 customer per hour. So we can serve 15 customer per hour on average. So you have to write it down. So service rate is 15 customer per hour. You cannot just write 15. That's it. No, you won't get the mark. Enter arrival time. Okay, now we need a little bit calculation. So what is enter arrival time? Because we know the arrival rate, we got 40 customers per hour. So how many hours we expect one customer coming? So basically 1 divided by 40, that's the 1.5 minutes per customer. You can write 0.025 hour per customer, that's fine, completely fine. But if you think this is not very easy to understand, you can convert it to minutes. This is 1.5 minutes per customer. But you can choose whatever answer, that's all okay, but you're gonna have to write down the unit, either hour per customer or minute per customer. Okay. So, and the next one, what is the utilization with 3 employees? So this is slightly, the next one is the service time. Yeah. Service time, slightly more and calculation, because the service rate is 15 customer per hour. So what is the service time? So how many hours we can serve 1 customer? That's pretty simple. 1 divided by 15, we got 0.0667 hour per customer. This is a quite weird number because you can convert it to 4 minutes per customer. But this is also okay. You can get a full mark for this answer, but this is just not very easy to represent, so you can just convert it. So you can do the conversion or not. That's all okay. So the last one is what utilization with 3 employees is system stable. So that's, and so far maybe we can calculate that for 1 employee. So that's basically lambda divided by mu. But if we don't have the 3 here, so 40 divided by 15, that's basically, that's basically a number higher than 1. But if we got 3, so we can intuitively think about this. 1 employee can serve 15 customers per hour. We got 3 in parallel. We can serve basically 3 times 15. That's 45 customers per hour. That's intuitively, but we're gonna talking about this later on in next week. So the rho is around 88.89%. So that's smaller than 1, so the system is stable. Okay, so this is just the first question for a real and final exam papers. You will get some equations like this, but that should be enough. We could make sure this is all enough for calculating all the questions. But you still need to understand, so the relationship between arrival rate and inter-arrival time, so what does it mean? So this is basically quite easy to understand. And also service rate and service time, what is the relationship between them? Okay, as long as you know this, that should be fine. And the complicated equations like this, I couldn't remember this, but probably give it in the final exam. Okay, so we are not done this question, but we're gonna keep going on this in next week. So this is just showing you one example of this waiting line system. Okay, so that's it. That's everything for today. And if you have any question, you can come to me or you can